dimension, we spell it squared. Right? Because again, we're squaring these guys. Right? We realize, okay, I have different dimensions here. Take care of that. It's not a problem. But then when I would do weighting, I might want to analyze position very strongly. Maybe I don't care about voltage. So the relative value of the Q term for position is what compared to the relative value of the Q term for voltage. I really want to penalize one state more than the other state. This is what about the relative magnitudes of Q? The structure of Q here too. Something we have done. So I have all these terms for Q. Q's here, sorry. And I might have zeros everywhere else. I'm going to make a diagonal. Does that make sense? It probably would be diagonal. It doesn't always have to be diagonal. There's a good chance it would be diagonal. That's because I don't have a penalty for position times velocity. I have a penalty for position squared, velocity squared, voltage squared, and so forth. Right? Not necessarily a penalty for position times velocity or position times voltage, although it could rarely occur. Right, so diagonal, okay? So if I really care about x1, don't care about x3, what's the relative value of Q1 over Q3? Which one's bigger? Q1. Right, that's one I want to really hammer. I really want to penalize that. I want to take care of the dimension itself. Anyone think of a nice way of maybe defining these Qs in terms of something? For instance, maybe I want to make sure that my position of my controller in the lab there goes within 1 degree max. Don't let it deviate more than 1 degree. I might have to define a penalty for that. Any thoughts? So, x1 is position. And I want no more than 1 degree deviation. How might I use that to find what Q is? Remember, the dimensions of Q's have to be 1 over whatever the dimension of x1 is. So if x1 is in degrees, this will be 1 over degrees squared. Right? So, anyone think of a nice way of maybe defining what Q1 might be? Wild guesses? Thoughts? Squared. Hey, this is my maximum value I want. One over my max value squared. Takes care of dimensions. Takes care of what I want. I want no more than 1 degree. So I'm just kind of nice maximum amount. Smaller my tolerance, the bigger that number is. Right? And do this all the way across. Very common way of doing this. velocity, I say, yeah, I want 65 miles an hour plus or minus 1 mile an hour. Don't want to deviate any more than that. Okay? I'll wait when it is. How about this guy? Let's get one of those. We do the same thing? Absolutely. Yeah. In fact, the lab system, you use what? What's physically is it? What's the input to that motor system? Be a current into it. So it could be, for that one, U R, U transpose R. U, and this might be just one current. Current, so this might be, what's the maximum current that has to come out of that thing?
It's 1 amp.
I think it's 1 amp. How much are you waiting on? I want to make sure I don't go past 1 amp. I don't care what it is inside there, but you know, I'm going to penalize it more than 1 amp. If the system was only 0.5 amps, I've made it an even stronger penalty on that. It says, boy, you really don't try to make that anything more than 0.5 amps. Right? So the smaller my constraint here, the bigger the penalty. That makes sense in these things? So I've taken care of dimensions, we've kind of taken care of relative things on this thing. Some of these might be, I don't care what the velocity is. So 1 over infinity is, of course, 0. And that's perfectly fine. But this cannot be 0. Because I've got to invert it. Yeah.
So would you use this to like keep from saturating your motor or something? Or
Yeah, absolutely. Yeah. So if I had a saturation, maybe it's a voltage thing, I'd have a voltage saturation or current saturation. This might be desaturated. Or I might want a little bit less of that just to make sure. This doesn't guarantee it won't saturate. It's just the more I constrict this, the more it's going to try to make it control that it doesn't get near saturation. Right? And the smaller I make this, well, really minimal. What kind of controller do I have? So it really becomes a minimal energy system. Because if you don't really try very hard here, right? You're real wimpy about it. The thing about that kind of makes sense for, say, cruise control car or remote car. What eats up your gas mileage?
acceleration?
Accelerations, yeah. You know, the old Jackrabbit starts in State Street, right? Keep really slow accelerations, you know, close, whatever. You look at these guys who do the max gas mileage competitions and stuff. They're coasting most of the time, you know, so as much as they can. It's going to be really, really slow acceleration because you're minimizing the input to the driving the car. Right. So these guys behind you are honking, flashing lights because you're kind of cruising out there from the red light, nice and slow, because you're trying to save gas. Of course, in this state, probably some of the lane of the light. I guess that's saving gas. You won't stop. And that's also a thing for traffic control. You know, ideally, you like to have everything times so you don't have to slow down. That's, again, also why general cruise control gives you better mileage because it's keeping it close. So, questions and stuff can make sense? You're going to be doing now we'll give you the equations for it all. So let's think of them.
The angle?
Yeah. Angle defined from, well, it's defined the origin here. What else?
You approach it as you as well?
I have to penalize you, just in recording purposes, I have to make sure that's non-zero, right? I might make that, you know, since it's being driven by a max of 1 amp, maybe some penalty on that, make sure I don't hit saturation on that. So I'll penalize you, right? What else?
The real system is the center of the track.
Yeah. I want to penalize how much deviation I have here too. Because otherwise, it potentially run off the end. That's up to the linear system. You're balancing your baseball back here. You know, if I have to keep moving like this, eventually I'm going to hit the wall. Right? I don't want that, so I'm trying to keep this guy centered here too. Which one do you think I'd penalize more? Theta or X? Maybe X. Keeping it centered versus keeping it balanced. I might go with theta more. You know, I'm going to theta even if I have to move a little bit more. Anything else? What about velocities? Don't get velocity? No, maybe not. You don't really don't care how fast it goes. So what might be a Q matrix for this? So our states, get rid of what we have in the lab. Might be a theta, theta dot, x, and x dot. Our states. And our input is some current. What's the possibility for a Q? That's waiting states.
So it'd be 1 over theta max squared, is that what we're saying?
And you can find what max angle am I willing to accept? What might be the limitations on that?
Well, we can't go beyond 90 on that.
Well, actually you can. You can make a controller where it starts off hanging upside down.
Oh, okay.
And we'll flip it up. But getting the big angles, what's the problem?
You'd go too far on
At
X.
the moment, to get that thing back up, trying just too hard to get the thing back up. And so you're get the baseball bat way over here, and then you're running, you can't run fast enough to catch up with it. Right? All right. What else might limit it? Well, our differential equations make linear equations for this. Small angle approximation. I might want to make sure I don't violate my state equations by going to the non-linear region. All right, press as much as 0. Yeah, that's fine. Theta dot, maybe I don't care about that. We'll put a 0 in that. What might limit the X position? Away from my track. Now this one's one of the lab rotaries, if you don't have that problem with, but it'd be some max motion or that. And maybe I don't care about the velocity. So that's a perfectly valid Q matrix for this. R must be non-zero. And I might put in something there, it's just like, I want to try to avoid saturation, maybe I'll try to penalize it so no more than kind of 1/2 the saturation. Something like that. You try different things. But the more I limit this, can you think of what the behavior might be? If I really penalize my input, what's going to be the response to my system? Swelling. Yeah, but that's the thing from there or whatever. Versus, it's going to turn really hard. It tries hard, and you disturb it point, because it's right back. It's going to try as hard as it can, especially also with these guys. These are going to be rock solid. Looser I make this, solver it's going to be. What about the poles of this closed loop system? Where are they? Unstable. No, they'll be stable. Yeah, this is actually guaranteed. This Riccati equation is a satisfactory solution for loop noise. Will be stable. But where are they? I don't know where they are. Right? They could be anywhere. Because I haven't defined what the poles are. I said, I want to make sure that I define the penalties for the gains. Poles and where they are. They might be fast, they might be slow. But I do know they'll be stable. That's the only thing I know about it. How can I find out what those poles are? No. Come here, you've got a closed loop system here. A matrix. Right? How do I find the poles for that? Yes, I minus A. Yeah, find the characteristic equation. So in MATLAB, it's what? I can notice. But I can define where they are. They could be anywhere out there, which can be a problem. Right? This is kind of a start. We'll do some examples next time. Show you a real friendly example of very close. Fortunately, when we actually do this in MATLAB, it's a piece of cake. It's really easier than full plane.
Same as last squares.